So quantum computers are expected to deliver speedups over classical computers for certain tasks, right? Nevertheless, the present-day quantum devices in what is called the NISQ era are too small and noisy to execute fault-tolerant problems nor error-correcting codes. So the question is, do we have to wait for the fault-tolerant era? In this context, BQAs kind of provide an answer saying we can try to use current quantum hardware plus a classical optimization loop to try to get something around the noise and use it. So the idea here is using parametrized cost function that encodes the solution to some problem and efficiently evaluate this cost function using a quantum computer and optimize using a classical optimization loop. And the hope or the mission for BQAs is to harness the power of quantum computers in the NISQ era. In this context, a problem arises. In some situations, variant plateaus have been shown to appear in the optimization landscapes and compromise trainability. Let me briefly, although I will give a precise or more precise definition of variant plateaus later, let me say that it is a statement about the scaling of the average of the partial derivatives over the whole landscape. So this scaling is exponentially suppressed in terms exponential in the size of the system. And okay, the question is, do variant plateaus forecast a winter for variational algorithms? And we will try to answer if there are ways of going around this and whatnot. So let me begin with a connection between BQAs and quantum optimal control theory. So the standard problem in quantum optimal control theory can be thought of, for example, guiding the evolution of a state, of a quantum state, a quantum system. Suppose you have a quantum system that evolves freely under some Hamiltonian H0, and you want to guide the evolution, for example, target another state at the time t. So what you can do is introduce new terms in the Hamiltonian that are weighted by these theta functions that we call control fields, and these HKs are Hamiltonian generators. And the idea is that these control fields are called fields because they are usually associated with interactions of the quantum system with, for example, electromagnetic fields. So in a semi-classical approximation, you just neglect the other system and you consider like a classical theta function that is shaping some interaction, shaping some Hamiltonian here. So so suppose you want to achieve some desired evolution. You need to shape these functions. Okay, searching in a functional space is very hard because if you parameterize this whole functional space, it's infinite dimensional. So the first thing people do is you parameterize with final dimensional number of parameters. Then you define a cost function and minimize it to find the optimal protocols. And let me introduce a certain kind of parametrization that is usually chosen. So it is the so-called piecewise constant controls. The theta k functions are considered constant over some periods of time, and they only change like in a quench way. Okay, and in this case, the Hamiltonian is always when it's not in a changing point, it's time independent. So each of the propagators, instead of having to solve a complicated time evolution equation of motion for the propagator, you already know what's the form of it, and it's just exponential of the Hamiltonian at each of the time steps. for times the size of the time step. So this is easy, and then the action of the control over the whole period of protocol is just the product of each of the layers. And this is very similar to what happens in some kind of PQAs. For example, the QAOA and hardware efficient and the HVA and many of them, of the famous ones, they have a periodic structure. Okay, they have like layers with same kind of generators that you repeat over time. And this is the way we will designate all of them. So it's each layer is just a product of gates that are exponential of some Hamiltonian generator HK, just in the same spirit as in the control case. So in a generalized, both approaches can be pictured in a generalized framework in the following way. You input some state either into a quantum computer or into a, I don't know, quantum system. You start like applying electromagnetic fields, and you have layers that share the structure, and you repeat this lot of layers, and at the end of the day you have a state you measure, and you repeat this a couple of times, so you estimate the cost function and the gradient, for example, and then you use your favorite classical optimizer to descend over the gradient and optimize your cost function and minimize the cost function. The point I want to make here is that if you choose the same set of generators for both approaches, the expressible evolutions of the system are very similar, if not the same, when you are in fact they are the same if you allow for a lot of layers and a lot. They only differ in the single layer. The single layer is, in one case, is, as I said, is the exponential of the Hamiltonian at each time, and in the VQA case, it's just this unitary but trotterized. Okay, but in the long run, if you have a lot of layers, BCH formula will make sure that at the end of the day you will generate very similar unitaries, or the things that you can access are very much the same. So my message from here is that the circuit and the quantum system, the control system, are fundamentally determined by the set of generators. Okay, let me briefly talk a little bit about barren plateaus. Consider what are barren plateaus about. Suppose we have a state rho, a density matrix, and we want to estimate the probability of being in the zero state. In theory, what we do is we take matrix multiplication and we take the trace and we compute this exactly. But in practice, we need to prepare a number of copies of rho and then make measurements and estimate as the quotient of the times I get zero over the whole number of experiments, and this has statistical precision of 1/√n. So, and in this context, the non-mathematical definition of barren plateaus can be the following: that the cost function will become exponentially small in average with the system size. So, for example, consider I have a partial derivative that is dc here, that is, I consider it to be order 1/2 to the n. To resolve this partial derivative, I would need a precision of at least that order. So I would need n, the number of shots, to be order 2 to the 2n. And this, you can see that it grows double exponentially, and very quickly, for example, for n equals 20, you will be reaching a number of shots needed to resolve it properly, at least 1 trillion shots. So this is unattainable. You cannot do this. So what you end up doing is, if you don't have that many shots, you don't resolve the partial derivative correctly, and you do random walks in parameter space or in the landscape. So it is crucial. So you will not be able to scale properly your technology, your circuit if you have a Variant plateau. So you need to determine which conditions allow them to arise and try to predict their presence. Okay, that was our goal in this paper. So let me come back to the idea of quantum control. Remember, suppose you have different choices of your whole parameter vector, 1, 2, and j. Each of them generates a different final state. So the question is, what is the set of possible reachable states that I get when I vary my parameters? For all possible choices of parameters, what is the set of all reachable states? And this is well known in control theory. And what you need to do is take your generators and compute the so-called dynamical Lie algebra. That it is the Lie algebra that you get when you start doing commutators, nested commutators between the generators. So a commutator is a map between maps two operators into a new one. You start mapping and getting new operators. You put in a bag, and the bag sometimes new elements that you put inside, they are not linearly dependent with the ones before. So what you do is you put a lot of them, then you like kind of find a linearly independent basis, and then the span of that basis will be the Lie algebra. The Lie algebra is a vector space plus that is also closed by commutation. Now, once you have the Lie algebra, the exponentials of the Lie algebra elements in this vector space, if you exponentiate any element of this vector space, you will get a unitary, and this unitary is in principle expressible by your system. So all of the reachable unitaries form a Lie group. That is this, we denote this with this G, that is the exponential of the Lie algebra. And the set of reachable states will be an orbit given by the action of the group over the initial state. So different initial states will give different orbits under the same group. And for example, like for you to start grasping this, in the case that you have, for example, if your circuit is universal, what is called controllable in the quantum control case, so you can generate any unitary in the unitary group, your algebra will be the whole unitary algebra, and the group will be the whole unitary group of degree d, of your d being d your dimension. But in the general case, G will be a subgroup of the unitary group, and thus your controllability will be reduced. Not every evolution will be possible. The bigger is G, the more expressible is the control system. So a schematical picture of this is, we start with some parameter space with n parameters. The unitary, the circuit maps this into unitaries that are that belong to a Lie group that is inside unitary space, and is given by the algebra that in turn is defined by the set of generators. Then you act with this on a state, and at the end you finally map this into, using a cost function, you map this into the real numbers. And again, the action of any possible circuit with the generators G will be contained in the Lie group G.
Sorry, like, can you like
Yes, please.
get both? I mean, this is like very important slide, right? So first you have like, parameters, like, I mean, which we normally, like, I mean, we can tune, right? I mean, and then, like, how do you go from the parameter space to the, oh, I mean, so you encode these into your, like, unitary
Gates.
and that's exactly. So,
Mm-hmm.
so then we have this unitary and the choice of our ansatz will determine, the controllability and all those things about,
In this setting, we are only leaving, yes, we are assuming that the periodic structure is fixed, and then the only freedom we have to choose is the generators, right?
Correct. And then like, depending on the initial state that we have, the third picture is about, which quantum states we can basically explore.
Definitely.
Yeah, okay. And then some measurement has been performed and we get the loss function. Beautiful. Yeah, very nice. Yeah, like picture. Okay, yeah, thanks.
Okay, thank you, Kishore.
Yeah.
Okay, please stop me whenever you feel it's for me it's good to be in the same page with everyone. So let me present just a motivation for what I am for our results. Let me present some previous results, very recent but still previous results, that relate the expressibility of the ansatz of the circuit with the scaling of the gradient. And for this, just consider two sets of unitaries. One solving problem A and another solving problem B. So here we have a picture of unitary space, and you have two subsets that are green and red, each solve different problems. And you have your accessible unitaries are this other like, subset that is G, it's the dynamical Lie group. So you only intersect with problem A. Thus, you only solve problem A, you do not solve problem B. Then you go and look at the landscape and you see this kind of landscape. Now, if you start making your system more and more expressible, you see that this gets flatter and flatter and harder to train, harder to estimate the gradient direction. So this is from the paper of Holmes et al. Here at Los Alamos too. And we kind of have a similar spirit to that, but we relate this ultimately with something more fundamental, that is the Lie algebra that kind of determines what is the size of the Lie group. Okay, we go one step further. So before moving on, let me briefly tell you how to measure the expressibility of an ansatz. The statement the expressibility of an ansatz, it has to speak about all the possible choices of parameters, right? You're not saying, I chose this parameter, what's the expressibility? No, it's about arbitrary choices of parameters, what is the breadth of functions I can generate. So you need to think about the distribution of unitaries that the distribution of parameters is translated into. So to measure that and picture that, something that will be central here is the concept of hard distribution of unitaries. This is just a fancy name for the uniform distribution in unitary space. To measure how uniform you are distributed in unitary space, how expressible you are, you will use this expressibility superoperator that it is constructed from the subtraction of these two other superoperators that are called the teeth moment superoperators. That given a distribution of unitaries, they act in the following way. You make this, a superoperator acts on an operator to give another operator, right? So the teeth moment, it's supposed to measure the action of the distribution of unitaries it's supposed to measure the tth moment of it. So what you do is you take t copies of some operator O that you will introduce here. You make t copies, so you are in the tensor product space of t times your system, and you conjugate each of them by each of the possible unitaries in your circuit, and you integrate over that, and this will give you another operator, right? And then you compare that with what happens if you conjugate and integrate over the hard measure. And if that is, and the idea is, okay, if you want to see if this whole thing is up to second or up to t moment the same as hard, what you need to do is take a basis of operator space and act on all of them. So a similar thing you can do is just take the norm of this thing. For example, you can take the infinite norm and ask it to be 0. If the infinite norm is 0, then you will say that U forms a T design. And here I am saying 2 because in the case 2 is the one we will be interested in. I hope this is clear. It's usually hard to understand. Please let me know if there's any.
Sorry, like trying to understand it. So basically, the Tth moment super operator there, basically you are, I mean, the measure that you are taking. What's that measure? I think in the first one you have the hard measure, right? The one which have
correct.
And the second one, like the
your distribution of unitaries from the ansatz.
So
exactly. Yes, it's integrating. You can either look here, integrate over parameters over your parameter possible region of like parameters. You integrate, and then this thing here kind of how many times each unitary appears will kind of be like a measure. So you can either do that or first pre-compute some unitary distribution and integrate over that unitary distribution. So yeah, it would be more clear if I put a unitary distribution here, because it's just the same, like here the hard one is integrating over a unitary distribution.
So then we take like basically a difference of two super operator, and basically we have like t moment expressibility super operator, because we are kind of like taking the difference. So and this operator could be anything, right? It need not be positive or something, right? I mean, it can be
yes, I'm not sure. I guess it can be anything. All I know is if you take the moment the norm of this, and this is 0, it means that acting on any operator will give 0.
Exactly.
Okay.
Exactly. Yeah. So we kind of like looking at just the deviations. Okay.
Correct. Yes. And the thing is, we want to know if we are our ansatz is a 2 design or generates a 2 design or not, because this will be key for our theoretical results. And let me explain why I mean this. So Variance plateaus are all about
Martin, sorry to interrupt. For the previous slide, it's a high A. After we take the trace of this expressibility, do we want it to be high or low? Like in the end,
it just depends. If you want to make analytical calculations, you want it to be low, because I am about to show you how to make the analytical calculations. Now, if you want, now you will see, but in some cases, if you want to avoid Variance plateaus, you want it to be high. But you will understand this in the following slides, I guess.
Thank you.
But if you want to give analytical answers to something, you better be you better form a 2 design, and let me show you why. So it's okay. Do you wanna you want me to? Yes, sure. Okay. So I was saying that the Variance plateaus are all about the variance of the partial derivatives. So let's compute Variance plateaus. Let's try to see if we have Variance plateaus. So how do we do this? the variance of anything is the square, the mean of the square minus the square of the mean, okay? And the mean here should be understood as the mean over the landscape, over the parameters, integrate over parameters. Remember that C is a function of theta, so this is an integration over parameters. And this I am not considering because it is easy to see that this is not suppressed, but it's always zero. At least for the cost functions that the cost function that we are assuming, this is straight zero. The landscape, the average of the cost function is zero. It's not tilted. This is the only thing it's saying. But more importantly, this term will speak about how much we are concentrated into that zero. So remember that this is the cost function. And now let me take, so for you have initial state, you conjugate, and you get the final state, and then you measure some O. And now expand into a before and an after unitary. Just to before and after, why? Because you will put here, exactly here at the end of the before one, you will put the gate that you're taking the derivative with respect to. So all that it happens is the generator comes down and you still have UV. And then at the end of the day, the derivative is just this. So you have the conjugation of rho with the before one, and the commutator of the generator with the after, with the operator conjugated with the after one. So, but don't get very much into details. The only thing that you should pay attention here is that you have that the partial derivative it's the trace of some things, and when you integrate over parameters, this is what I was telling Kishore before. When integrating over parameters, some function of unitary depends on parameters is the same as integrating over the distribution of unitaries, some function of the unitaries. This is just like that. And now the nice statement is that this function is a function of like a polynomial function of u in to the power t, then you could replace and your distribution forms a t design, then it's the same. It's precisely the definition of a t design, right? That your distribution is indistinguishable with the hard one. So you can replace this integration with the integration over hard. And the important thing here is that integrating over hard is pretty well studied and known. And you have these expressions that are quite like simple. For example, integrate some function of u, the trace that is given by the trace of the conjugation of A, some operator A times B. This is just the trace of A, trace of B over D. When you integrate over the Hermitian, on the unitary group. So if our distribution of unitaries, we can assure you that if we can assure that our distribution of unitaries forms a two design, we can integrate and compute the variance explicitly. Exactly. This is what Google did. They assumed in the seminal paper of Barbatos, they assumed they have two designs and then they integrated here. And let me tell you that under reasonable assumptions.
Sorry. I think there is a question by Sai, probably like Sai.
Yeah. Hi.
Oh,
hi.
please. Yes.
Yeah, hi, Martin. So very nice talk. Thank you very much. I just, it's a silly question, and perhaps you have implicitly answered. But why Haar measure? I mean, so let's say that I'm just running a standard on a classical computer. I'm just running grape, right? And so I start with some random parametrization, and then I just let it basically search. Is it clear if you just perform these kinds of numerical experiments? Is it clear that the actual distribution of the unitaries that you would get in the different iterations of grape as it converges to the solution, that numerical experiment essentially replicates?
I'm not sure about that statement, because you are considering optimization paths. So I would say, forget about optimization, just sample your landscape, okay? And for each, so you sample parameter space, and then each of the parameters choices you get, construct a unitary that is, of course, using the circuit. And now put all of the unitaries in a bag, and this is your distribution of unitaries. And the statement is that this is or is not a two design.
No,
just
yeah,
don't involve, please don't introduce optimization, because I wouldn't know if the optimization paths kind of just what I'm saying, if they are some kind of biases of what. But it's not important, because the statement of Variance Plateau is about when you start optimizing. So how do you solve an optimization problem? You first randomize a guess, and then you start taking derivatives and following the gradient if you want to be simple. And this is the statement is that, okay, if you have a Variance Plateau, you will randomize your guess, and when you compute the gradient, you will not be able to resolve it properly. So you will never find correct direction, and you will make random walks.
Yes, of course, Martin, but you could also basically argue that, okay, maybe what Variance Plateau teaches me is random parametrization. Initialization is a very bad idea. But I could be inspired, let's say, by, in this context, I could be inspired by matrix product methods or approximation techniques, mean field theory, and I could produce basically an ansatz. I could start with an initialization, which is essentially solving a simpler approximation of the problem, right? And then I'm not really starting with a random field, I'm starting with a very specific field. And so I don't see it, but maybe we can discuss this offline.
No, sure. I mean, we are assuming that you are not doing anything fancy. All of our work is based on the easy way of doing. If you have better ways of designing your initial and whatever, I mean, I cannot say anything about that.
I see.
Of course,
I see. I understand.
Study that. Anyways, I think solving a simpler problem before, it's a good idea, but you need to make sure that the simpler problem does not have Variance Plateau too. But anyways, if not, like just solving a previous problem, or like initialization to me sometimes feels like already solving the problem, like finding a good. I mean, if the statement of Variance Plateau is that you have like a big flat landscape and you have like a very narrow gorge somewhere, finding that seems, it's not obvious that a simple problem will then properly generalize to that one. You surely will be able to solve the simple problem, but it's not obvious that will be helpful for the complicated one.
I agree. It's just that I don't understand how the argument about the curvature of the landscape is being made on the basis of Haar measures. That justification is what I'm not understanding, and I'm just trying to understand, because if you basically make the argument that hey, in a real experiment, when you simulate, you've asked me to keep optimization out, but in a real optimization, you run through, if you sample basically the space of unitary operators according to the Haar measure, then okay, I agree. Then I basically have to concede that the Haar measure is the way to go, and then the t-design is just an approximation of the Haar measure, right? And rather the other way around we go, because the Haar measure
Correct.
is easier to calculate. I failed to see the argument, Martin, but maybe I just don't understand something very simple. Yeah, I'm happy to kind of just offline this discussion.
Yes, of course. I would be happy to. And let me. I brought another slide that I didn't include in this one, but maybe it makes it clearer. What's Variance Plateaus? You have this Shapeshape inequality for some random variable x that it relates x with. So suppose what's the random the value. So suppose you take your partial derivative from. You sample partial derivatives from the landscape. Now, the probability of the partial derivative to deviate from the mean, that is 0, that we already said, substantially, that is, like, for example, more than A, will be the variance of the partial derivatives divided by a squared. So this is the statement of Variant plateaus. You will have, so if this is exponentially suppressed, like you will need, like it will be very, very, very hard for you. So this, like very, very hard for you to find a partial derivative that deviates substantially from zero. This is the idea. But
sure, I'm just arguing that I don't understand that both sides are, you know, the average and the variance are computed with respect to a probability distribution, and I'm just arguing that the correct probability distribution is the one that appears in the experiment and not the hard random one. And but you know, this difference we perhaps
yeah. Okay. I see. I will show you some of our results relate the actual distribution that you will find. Of course,
fantastic.
We are under assumption, right? But let me continue a little bit. You will see what I mean.
Yes, thanks.
I'm just about to get there. For example, okay, as I was saying, for a second, suppose that your answers converge to a 2D sign, then you do this integration and you will see that this thing, when you put this here, you integrate, you get like this squared beneath, and it is easy to see that this will like kill everything you have on top for reasonable assumptions on the norm of the operators. So my statement is, if you have a 2D sign, the variance of the partial derivative will be exponentially suppressed for reasonable assumptions on rho and O. So one of our theoretical results says that if you have a controllable system and you have a scaling, if you have a controllable system, there is a scaling of the depth of the circuit that allows the distribution to form epsilon approximate, so to be very near to a 2D sign, and thus exhibit a Variant plateau. So the statement is, you have controllable system and you have enough, there is a number of layers that is enough for you to converge very closely to a 2D sign and thus to exhibit a Variant plateau. And this builds directly on a previous also result in this paper. I just say previous because it's in the way it's presented, that it says that it relates the depth of a controllable system, the depth it needs to have for you to form epsilon approximate to design. So you can play with this. This is the expressibility of a single layer. So making assumptions on the expressibility of the single layer, for example, being very, 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 like, in sense bad, very near to one, that is like very not expressible. So the zero is the 2D sign, right? I'm saying, suppose it's polynomially close to one. And in that case, it is easy to see that a polynomial number of layers will be enough for you to start departing from one and approaching zero in sense of the whole expressibility of the answers, not of the single layer. I don't want you to boggle a lot into these details, but the statement is, again, polylayers for a controllable system should converge to 2D sign and thus have Variant plateaus. This is the takeaway. And in practice,
sorry,
yes.
Martin, like, yeah. So I mean, in the first case, your super operator, you look at the infinity norm of that, and when that's epsilon, you call it like, I mean, that's, yeah, like that's the definition of the epsilon approximate to design. And that epsilon basically enters in the number of layers that we require for periodically structured answers. Right?
Correct.
So when like epsilon is very small, like let's say, like 10 to the power minus 6, then that's good, right? I mean 10 to the minus 20 or whatever, like better than the number of layers. I mean, so what does it say? Like, I mean, then the number of layers circuit is to have what? Like I mean, what is the complete statement? Because you say that when the number of, then what happens?
when the number of layers is poly in the size of the system,
then it forms a block.
It forms a 2D sign, and thus
Okay.
you will see a variant plateau, because you can integrate and you can analytically show that the system will have variant plateaus
Okay.
for reasonable assumptions on O and rho. It's difficult to say that.
Correct.
In practice, you will see this happening much faster than, like, it's not poly. Just like linear will be enough. Like all of our numerics is linear and it's very well converged. You just don't see new things happening. So
sorry, like can you just like again, like this is a very nice slide. So basically, like, you need these many depths to basically have epsilon approximate to design, so that you can make analytical statements, right?
Exactly.
So this is required to make analytical statement, and then in that case you can conclusively say that it has variant plateau or not have variant plateau, because you can do all those integrations.
Correct.
But then, like, in practice it could exist even before, just that we are not able to say that. I mean, but it could exist. I mean, that's what you're
definitely.
Beautiful. Thanks.
Yes, there are very little. There's a paper by Samson, Wang, Marco, and the people of Los Alamos that they show that log n depth with the hardware efficient ansatz, you don't have variant plateaus. So my expectation is that log n maybe like anything below, so order 1 or order log n could be rid of variant plateaus, but after that it's just like very hard to be able to train, probably. So just let me okay, this is just some examples of choices of generators that lead to controllable systems, or call it universal systems, that they allow universal quantum computation. But of course, and this is important, this statement is not, you're not def. I am saying that linear depth is enough for you to convert to design. And you clearly do not get universal quantum computation with this kind of like systems with linear depth. You will need an exponential depth to be able to produce all of the unitaries that are expressible in the unitary group. So it's not, I mean, my point here is that you are not, this is important, that you don't need hard random to have a variant plateaus. You only need to design. And to design, you can create to design with the discrete number of gates, for example. Okay, it's not truly uniform. It's just uniform up to second moment, and this is already killing you. So my thing is, my point is, don't associate this with okay, if I have I need to be able to access all of the unitary space. No, it's not that. It's not that. But it's already, when you access too much, you're already like killing it. So again, two examples. First, the hardware efficient, you can express it as in this way. This is slight modifications. We replace the entangling gate with this kind of interaction, but it is easy to see it will be similar, and you can prove that this is controllable. But hardware efficient, you also know that it is universal quantum computation. So, but more importantly, let me talk about the second one. Here is the spin glass. The spin glass here. Suppose you have a Hamiltonian that is for a spin glass that is like this thing here, and you want to do QAA, so you put a standard mixer, and when you take the commutators within this thing and you construct the Lie algebra, you will see that this is like full rank, it's controllable. So again, this is a no-go argument for determining ground state energies of spin glasses using deep QAA ansatz, and with deep I mean linear depth QAA ansatz. Okay, Now let me tell you about how so controllable systems are very special systems, right? So let's start moving away from this. First thing we can think of is a weaker notion of controllability. So suppose you're not generating universal quantum computation on the full unitary group, but you're in the following situation. You have a symmetry. When you have a symmetry, you can characterize this by a Hermitian matrix A that commutes with all of your generators. And this means is that the unitaries that you will be producing in the eigenbasis of A, they are block diagonal. And the state space, it will just break into subspaces that are, because the unitaries are block diagonal. If you start in a subspace, you will never leave the subspace under the action of your unitaries. So they are called invariant subspaces. And here we can make a new definition. So instead of considering controllability in the whole space, just consider controllability in a subspace, universal subspace. So for this case, we can do something very similar to the things before and analytically integrate and have an exact expression for the variance of an initial state that belongs to some of these subspace, completely belongs to a subspace, and you have this expression. So what do you need to look here? This is the dimension of the subspace. These are the generators, and the K up here means that you need to reduce this to the subspace. And this delta function here is just the Hilbert-Smith distance between the operator that is inside and the identity. And let me, so this is the observable that you're measuring, and this is the state. And what this is saying is measure the distance of the reduced generator to the identity. And this distance will be, the variance will be proportional to these distances. And the important thing here is that if you have distances that are exponentially vanishing, you will have barren plateaus. So these are different sources of untrainability. And for example, if you have a global measurement, when you reduce to subspaces, you may have this thing being exponentially suppressed. So this is you can think of the result for global cost functions as being expressed here and whatnot. Like if you have an initial state that when you reduce, it's very near the identity, you will also have barren plateau. But in the following, and this is just, we will concentrate on the first term.
Okay, so sorry, like,
yes.
So Martin, like, I mean, this is quite beautiful, like, I mean, it captures many of the existing results already, right? I mean,
yes,
in some sense. So basically then you have variance, and I mean, for the periodically structured ansatz, I believe this result is right. I mean, the expression that you have got, and it looks for like the Hilbert-Smith distance for all of them, like, you know, they are whatever, I mean, so the generator determines your ansatz, observable determines the nature of the loss function, which in the Markov result kind of was there, and then the rho basically kind of determines, you know, like which the expressible, I mean, which states you will be exploring with the help of that, and then and the dimensionality dk, like, I mean, it kind of related to the number of qubits. So together, all of them, you know, like, I mean, maybe one can focus on them in a very nice manner to, you know, like take this quantity higher. And obviously this dk is larger, right? So I mean, sorry, dk is in the denominator. So you want that's why, like, at a large dimension, you have this barren plateau problem. But if we somehow make this, you know, like the first three distances large, so we want to be very far away from you know, like mixed, maximally mixed state, right? I mean,
yes,
yeah, like
yes,
in the Hillman,
yes,
yeah. So if, and this kind of fits very nicely with the paper, you know, like by I guess Nathan Weave and others, where they say that if you have entanglement, that can lead to, you know, like if you only measure subsystem, then part of the remaining is kind of, you know, like mixed state or something. And
definitely it's the last term here.
Okay, okay, beautiful.
Yes, but when you I guess it's I haven't thought of it like actually like in detail, but it's a nice thought. And I agree with you. Like you could try to save the day by making these things like big, but okay, you could try. Like, I mean, we gave like one of the corollaries of this theorem just makes very reasonable assumptions on the scaling of these things, and it appears that it's not easy to save the day with this. But
you don't have any summation over k, right? I mean, so you have like, you know, you break your h in terms of hk. Yes. And like, so there will be the hk, they will belong in different dk. Like for every hk you have a dk, right?
Sorry, can you repeat?
So what I'm saying, so now you have h, and you know, like based on the symmetry that you have, you write your like okay, your Hilbert space. Basically you write it down in terms of, you know, like all of these invariant subspaces, and the dimensionality of each of the invariant subspaces, that will be different, right? I mean, yes. So some of them will have, you know, like d1, d2, d3. So yes. So I mean, the left hand side, I mean, do you do any kind of summation here? Because what I see that you have one dk, but maybe, I mean, I should expect some summation or something, or like, you know.
No, because you are assuming that your state belongs to that.
Okay.
It's hj. I'm so sorry. Yes, I should put h. Sorry.
Okay. I see. So then it's very nice if the state belongs to a subspace whose dimensionality is small. Then you will not be able to explore. You will not have the
exact. That's what we do in the numerics. We pick the x exit. Let me show you if you want. I mean. I removed a lot of that because I need to include the overparametrization part, but but it's okay. We can leave that for another day, anyways. I don't know.
I mean, definitely. I mean, we could have you, you know, like, I mean, we can in 2 weeks.
Yes, this is in the case of x exit Hamiltonian. It's easy to see that it commutes with magnetization, and you have this. So magnetization is like you can say like spins pointing up. If you have all spins pointing up, you have this d0 here, for example, that is one-dimensional. If you allow one spin to go down, you span a subspace of like n states, and this starts growing. So d2 will be n squared, but here it goes like the combinatorial. So the half of the excitations subspace, this is exponential. So you clearly see that if you start with like a half excited state, you can you get Barren Plateau. But if you don't, if you have like stored with order 1 excitations, or I think it's enough to, I know, but if you don't, and you can see the curves like, but very, so this is the ansatz, nothing new here. These are all poly excitations. So 1 excitation, 2, 3, 4, 5. These are not poly, order 1, sorry. And you see all of them poly decay. You see the curves doing like, trying to do like this. The points here are the points are numerics, the curves are theoretic. So it's like exact. Like we expected this because it's a theorem, but it's getting the conclusion here is that the numerics are well converged, because again the theoretics assume convergence to 2 design, and the numerics, okay, you just set some depth and you just integrate over the landscape. So linear depth was enough for this to be like matched perfectly. And I mean, that's it. Let me go back, but I just wanted to show, and the n over 2 subspace, you can see that it's going down like exponentially. Okay, and the other one I show here, it's a one that is not controllable, but the algebra is still exponential. So we don't have theoretical results, but you already see a correlation there.
Thanks.
Okay.
So I just wanted to quickly comment, Martin, the formula that you just showed for the subspace controllability. Yeah, so these Hilbert-Schmidt norms, you can upper bound them, right, for kind of any operator and so on and so forth. So there should be, I mean, to answer kind of Kishore's question more directly, it should be possible.
I think so. I think you're right. I mean, I right now I don't remember how we did the proof for the corollary of this theorem. There's a corollary that says that, again, I don't let me quickly show you if you want, but we make some like basic
infinity norm is an easy bound.
We assume that the trace of the generator and the trace of operator to the fourth is like exponentially growing or whatnot, and we see that in this case, again, if the cost function will exhibit variant Plateau for any subspace that is exponential. So and if you want, you can come to the paper and look at and here I will probably look at it and remember what was the argument there. But I agree. We use bounding on the normal plot.
Sure.
So takeaway is that exponentially growing and controllable subspaces lead to variant plateaus. And now, okay, we still in very limited kind of systems, controllable and subspace controllable. So let's try to go beyond that. And I propose a very simple experiment. Suppose I take my dynamically algebra to be different representations of a common algebra, for example, SU2. So I take SU2 representations of SU2. You can think of, for example, the Pauli matrix is acting on a qubit, but you can also think of the spin 1 angular momentum and spin 3/2 1 angular momentum and whatnot. Each of these, you can build any dimension representation of SU2. So this will be D times D matrices, but again, their commutation will be three-dimensional. The algebra will be three-dimensional. And you can, because of the simplicity of this problem, instead of using hard, random, and whatnot, you just do the math like straight away, and you can find an expression for the variance here. And the important thing here is the variance is constant as a function of the dimension. And what else was constant? The dimension of the algebra. So before we saw that the variance was vanishing with the dimension of the algebra, because the dimension of the subspace is directly related to the dimension of a controllable algebra. Dimension of a controllable algebra is D squared. Okay. So we are kind of led to declare that actually the variance is connected with the dimension of the algebra in the general case, and inversely connected, right? So such that polydimensional algebras will exhibit or will be able to be free of variant plateaus, and exponential algebras will not be able to be free of variant plateaus, will have variant plateaus. And the takeaway is you can diagnose BPs by looking at the algebra now for general systems. You don't need controllability. Any system that is on the form of a periodic structure, you can look at algebra and try to diagnose BPs for order linear depth and more. And you can tune the generators to achieve polyalgebras and thus be able to produce very deep circuits that are free of variant plateaus. So for example, you can look at the transfer field leasing model. The transfer field leasing model is you have neighboring interactions, CC interactions, all captured by a single parameter, and then you have a layer of single qubit X gates. So this is very like a QoA for a graph that is a path graph, okay, or a ring, like if you can connect these two, but whatnot. So, and then consider the called longitudinal transverse field leasing model, where you apply another field, another like magnetic field that now it's in the Z direction. So this very slight change to the ansatz leads to a very different situation at the algebra level. One is polynomial and the other is exponential. So you can go and compute the numerics and compute the actual variance, and you see that, so again, you do not have analytical results for this, but you have a kind of guess, a polite observation. And you see that this works properly because the exponential algebra has like exponential decay on the variance and the other polynomial. And this is very far from controllability. So the message is very slight modification leads to untrainability. Be sure that you don't have exponential algebras and try to be, this is a tool for trainability aware design of ansatz. Revise your ansatz if it leads to an exponential algebra. And another example is maxcut. We generate random graphs, and then we try to solve the maxcut problem on each of these instances doing QA with this kind of set of generators, of course, and cost function. The random, we take well, the important thing is that most instances have an exponentially large algebra, and most instances exhibit exponentially vanishing gradients. As you can see here, the variance is exponentially decaying on average. So this kind of means that on average, the most instances will not be able, you will have barren plateaus on average, like most of the instances. And more importantly, our observation is corroborated. It's again that because these two things are inversely related when we plot the variance as a function of 1 over g, you see a straight line. And this is like, none of them is controllable. So you're very far from controllability and from being able to predict something analytically, but you still see the relation that is expected. So conclusion is, maybe maxcut is not the best problem for near-term quantum advances, at least not with BQAs with more than 1 or log n depth. Okay.
Sorry, Martin, just can I ask a quick question?
Please go ahead.
Are you making the case that if you want to use this parametrization, that what you want is basically somehow to luckily have your solution be in the orbit of a subgroup or a subalgebra, and not the
correct
orbit of
yes.
a subgroup and not the full group. And so those are the kinds of problems that you can solve.
Correct.
That's interesting. That's an interesting observation.
Definitely, yes. That's the idea of QA.
Would you know a priori? Like, I mean, if I just gave you a kind of, I mean, machine learning is not typically structured in an algebraic fashion, right? I mean, if I just say, please find me the best, whatever, like, search me the best path to whatever, would you know whether
best path in Hilbert space, you mean?
I'm trying to avoid traveling salesman, but like I'm basically just saying I have a classical problem. I'm trying to avoid kind of setting myself into complexity theoretically idiotic questions. But all I'm saying is that if I have a machine, if I have a function that I want to optimize, is it knowable to me that if I express, let's say, the SU2 subgroup of SU2 to the n, that the solution is in that subgroup?
No, it's definitely, I agree. No, I mean, that's
Okay.
the whole problem here.
Okay.
And you are nailing
It's not even
because now
theoretically
now
doable.
our message is use polynomial algebras. But the question is, okay, but what can you do with that? This is open, definitely open. I don't know. I don't know the answer.
I see. Very
But
nice.
it's what you can scale. So it's better try to constrain you to that, because
instead of expressibility versus trainability, you basically have this,
but that's, yeah, but that's
uncertainty.
reasonable, right? It's reasonable that you're not able to solve all the problems with the same. It's like not every there's a funny phrase that I'm not remembered, but you cannot solve open all the doors with the same key. You need to have a tailor-made answers for each problem, and this is the thing. Yes.
Some kind of no free lunch theorem.
Yes, definitely. Yeah, definitely. And you will see that this gets even worse. No, this gets worse here. Let me show you why. Before moving on, let me say that all the previous and the following results, you should view them in the sense that they work or they generalize very easily in each of these three fields: quantum optimal control, VQAs, and QML. And I say just directly work or easy to generalize probably. And for example, in particular, note that we assume throughout a linear cost function. And this is not the case although some ansatz, some proposed ansatz for QML are very similar to VQAs in the sense that you're just using a quantum neural network in the form of a parametrized quantum circuit. The cost function at the end is definitely not linear. So it's interesting to think what happens if I use a non-linear function, for example, mean squared error or log likelihood. And in that case, you should see this paper. It's very nice. And from Subhanu, that is, I think, here in the audience. And they analyze what happens when you have this kind of QML functions, and they extend the previous BP results to that regime. Okay. Having said that, let me speak a little bit about the second paper on overparametrization. So I don't know how I'm doing with time. It's probably terrible. Should we? I go very fast over this?
I think it's fine. I think it's fine. Yeah.
Okay. For me, it's fine. I mean, okay. So the training of neural networks, it's known to be hard in general, in some cases NP hard. And nevertheless, there are some regimes, for example, when you use more and more parameters than training points, that could lead to the so-called overfitting. However, in this regime, low generalization error is usually observed, and this is usually called overparametrization. In the overparametrized phase, the optimization problem appears to be easier. And these are, here I show you some papers that in quantum machine learning are starting to analyze overparametrization. And my picture is that the landscape goes from being hard to an easy optimization problem. Okay. But we will try to produce a unified, because these observations are usually, I would say, specific or for like empirical or whatnot. We'll try to tackle the grounds of the overparametrization phenomenon. So let me begin with the quantum Fisher information. This is known to be a metric for the parameterized state manifold in the following sense. Consider some notion of distance between states, for example, the fidelity. And if you tailor expand the distance between a state given by parameter theta and a perturbation of the parameters, you tailor expand it, and what you get here is the quantum Fisher information. as a kind of metric guiding the departure from zero distance. So the rank of the quantum Fisher formation in this setting. So if you eigendecompose it, each of the non-zero eigenvalues and associated eigenvectors will correspond to different directions in the parameter state manifold, parameterized state manifold. So the rank will measure the number of independent directions that your ansatz is able to access. And a fact is that this rank is always bounded, because the matrix is M is the number of parameters times number of parameters. It can be arbitrarily large, but the rank is bounded in the sense that it's trivially bounded by the dimension of the Hilbert space. You cannot have more directions in state space than Hilbert dimension. But we will show that there are actually upper bounds on the rank that are way tighter, exponentially tighter, and we will connect it with this with again the dimension of the algebra. So algebra appears again in overparametrization. So this slide is kind of large. Let me try to go. Okay, so underparametrized phase is characterized by not being able to access all possible directions. And when I mean possible directions, I mean directions in the orbit of the state, not directions in Hilbert space. You already forget about all directions in Hilbert space if you have a small algebra. If you have a small algebra, you have a small orbit, and this is the ultimately by choosing all choices of parameters, you will at most be able to access this orbit. But so this is important. When I speak about possible or possible directions, I mean in the possible by the ansatz. So under parameterized phases, you are not even to access all of these possible directions. And I will go over this because it's the main message here was that there are two kinds of in the landscape. So the landscape, what's the landscape? It's the map from parameter space to real numbers of your cost function. The landscape is your cost function basically, and there are two kinds of critical points. You have so-called regular critical points, where being on a critical point is exactly the same as your gradient with respect the gradient of yes, this is important. Not always the critical point is the gradient is zero, but you need to think about the gradient of each of the maps in the composition of maps. Your landscape is a composition of maps, and what I'm trying to say here is that there's oh, I should have the other picture here, but you have a first map, remember, from parameters to states, and then from states to Hilbert, from states to real numbers. And this second map, you can think that this is the true landscape in some sense. It's the landscape of that assigns each state a number. And what I'm saying is this, in the case of regular critical points, the gradient of this second map is zero. But there are also another case of called singular critical points in which you don't need that to happen, but you can have problems in the parametrization that give you orthogonal possible states that are all orthogonal to this gradient. And this is associated with not being able to access certain directions in the state space. So as soon as you are not access all of your possibilities, a lot of local minima, new like false local minima will start appearing in the landscape. And it is a manifestation of a lack of resources. It can be fixed by putting more parameters, for example. So let me give a more like a pictorial representation of this, you have one parameter and you have this like cost function. And here you see a local minima, but when you put another parameter, it may be the case that new directions appear. And this is the way that when you start putting more and more parameters, the false local minima start disappearing, and you only get you only remain the true local minima of the map from states to real numbers. So the parametrization is you're kind of forgetting about the parametrization.
So Martin, just a quick question. In classical, in standard control theory, the argument is basically that this parametrization also can cause local minima to appear, right? Proliferation of local minima with higher dimensions is actually a known problem. So, so I ask you, in this diagrammatic illustration, right? I agree with you that a new direction appears to get rid of this local minima. But how do we know that that the number of local minimas total are not proliferating, in the sense that the new direction doesn't bring more local minimas with it?
Okay, it is a good question, and the answer is you are talking about standard of optimization or control, and here it's quantum optimization. It's far different in the sense that you are going through quantum space in the middle, and basically all I'm saying is I don't know if I have a very, very good answer to that, but it is my belief that if when you put more and more parameters in a certain sense, you cannot create more false traps, but you will only like decrease the number of them. In the limit, this is easy to see. For example, in the limit, consider you put infinite parameters, you have a continuous control function, right? And in this case, it is easy to see that number 2 is impossible, because number two means that, I mean, you cannot be orthogonal. There will be no chance of this happening. But maybe I can give you a better explanation later.
Sure.
Using, I have my thesis around there that I explain this better. Maybe we can look at that later.
Sure.
Okay. For the moment, let's assume that this is the thing that goes on. That I imagine that there's an ideal landscape that that with some like critical topology fixed, and when I put more and more parameters, I start approaching that landscape. That's the way I think of it. So question is, how many parameters do I need for overparametrization to start? And the answer is such that I can access all feasible directions in my orbit. That is such that the quantum feature information is saturated. And again, saturated, please don't think that the quantum feature information is full rank. This is nonsense. I mean, once you put a lot of parameters, you will not be able to full rank the quantum feature information. It will always be like singular quantum feature information. But the point is, it's saturated. You don't get new. What I have it? No, I had it before. Here. I don't know why I didn't talk about this. So if you make an experiment, you just sample randomly points in your landscape, and you just take the average of the quantum feature information rank. So for each point, you build a matrix, and you take the rank and you average over all points, and you start putting more and more parameters in your ansatz, and you see this grows linearly. So this is full rank, full rank, full rank, full rank, and at some point you cannot get more rank, and your parameters still go up, right? This is what we experience. So saturation is that point when you are saturating the maximum rank that the quantum feature information allows. So in a quantum machine learning implementation, we have states in a training set. For each state, there is a maximum rank that the quantum fission information allows. And our definition of overparametrization is the number of parameters. So a QNN is overparametrized if the number of parameters n is such that it allows for the simultaneous saturation of all of the quantum fission information. All of them, I mean one for each of the states in the training set. So there exists a place in the landscape where the rank here, that we should have a rank of f is r for all psi in the state in the training set. And with this definition, we can see that we can get this theorem that the maximum rank, this thing that the quantum fission information can have, is trivially show that it is bounded by the dimension of the algebra. Remember, there was a more trivial bound for this that was the dimension of Hilbert space. But our theoretical result is that you can bound this easily with the dimension of the algebra. So how many parameters do you need to use? Well, just use as the dimension of the biggest algebra that you have. And why you have more than one algebra? What do you mean? This G sub mu is just the part of the dynamical Lie algebra that each of the psi mu states has support on. So if the state has support on all Hilbert space and all of the invariant subspaces, this is the whole algebra. Or if there are no invariant subspaces, this is the whole algebra. Okay. The takeaway is that, okay, then this M, I could overparameterize QNNs that have polyalgebras using only polyparameters. This is a positive result. Use poly number of parameters, you get overparametrization. And I want to I need there is no animation here. Okay. So the capacity of let me relate this result with the capacity of the quantum neural network. So the capacity of the quantum neural network quantifies the breadth of functions it can capture. So there are various definitions of capacity. Here we take two of them, one by Tobias Haug and of course Kishore around here, and the other by Amira Abbas and IBM people. So we take both definitions of capacity and make a theorem that says that the capacity is always upper bounded again by the dimension of the algebra. So this kind of provides an operational meaning for our parameterization, that is, capacity is saturated. And let me show you in an example what's going on here. So I take some problem, put some number of parameters, and start varying the number of parameters and look at the training trajectories. This is the cost loss function value as a function of iteration of the optimization, average over, I know, a lot of runs, whatnot. And the point here is that when I put low number of parameters, this is like kind of gets saturated and it's hard to make progress, like code achieve like very low values. And when I start putting more parameters, there's a kind of phase transition here where I go from, I know, polynomial decay to exponential decay. So in this case, when you have like 22 parameters, you see like straight line, complete exponential convergence towards a global optima. And in my understanding, this phase transition is due to two effects. One, I told you about disappearance of false local minima. You can study this by looking at success probability as a function of number of parameters. Success probability is you randomize a lot of points in landscape but optimize, and you count the number of optimizations that ended in success in global optima. And now you make a probability or a fraction of that, and this is what we plot here. When low number of parameters, you don't you very rarely achieve solution, and when you cross some threshold, you get like certainty of solution, and this threshold is exactly the dimension of the algebra. So number one. Number B is that once you are beyond the saturation point of the quantum Fisher information, solution manifolds start emerging and grow linearly with the number of parameters you use. And this is also explaining the easy of training trajectories, because now the solution is not a point in landscape, but it's a whole manifold that is like easier to access. A comment: exponential algebras will need exponential number of parameters to be optimized. And here, importantly, we assume nothing for the theorem. We assume nothing about cost function. You cannot save the day with the cost function choice. You will need exponential number of parameters to overparametrize an exponential algebra or a universal quantum circuit or a controllable circuit. This means that the landscape will be very hard in principle with the best number of parameters you can use. So this is another problem for exponential algebras. You have VPs, but you also have very hard landscapes with like exponential many local minima, false local minima, that you cannot get rid of them.
So like, I mean, it kind of, like, I mean, if I am understanding it correctly, it fits very nicely with the Zoe Holmes and Kunal Sharma paper, like, and others, like, where they talk about this trade-off between expressibility and trainability, right? Because if we have exponentially large algebra, then we are able to, like, cover for any given state, you are able to cover, like, large part of Hilbert space. Then then at the same time, like, you have all these like to overparameterize, you need like too many parameters, and then that's
exactly.
Yeah,
exactly. So like I've recently discovered there are some proposals to avoid barren plateaus with like new choices of cost functions. For example, there is a very interesting one. I haven't like looked into detail into it, by Nathan Vive, about using Renchi entropy landscape or something, where the landscape is unbounded and thus they kind of apparently they show that they can prove absence of barren plateaus in this kind of. But even in that cases, I still think that you will have this kind of problem still. I mean, I don't know, but it seems to me that even if you get rid of VPs somehow, which I don't think is possible, but maybe it is, you will still have this like exponential hardness of the optimization. So I'd better try to design very problem-specific, small algebra ansatz, and we're giving like a very good thumbs up for that situation. So now it's the question is, look for problems that can be solved with polyalgebras specifically.
But I'm just wondering, like, okay, maybe a nice question for future, but like, I mean, so now one could, like, I mean, because so like we can train well, we can, like, whatever, like express well, and like, I mean, so basically we want those problems where, like moderate expressibility is enough to, like, take care of the problem. But then at the same time, I'm wondering that, like, it's like quantum advantage will be very difficult to get, like, I mean, it will require a lot of like ingenuity, like, problem specific tools and so on. So wondering that, like, it could be possible that, like, when like, the complexity of the problem, like maybe like the problems for which we can do this, the problem itself, like becomes classically tractable or something, like do you have some insights with respect to that? Like, I mean, we want to comment something.
I just come and go with my hopes about this, I have no definite
That's good. Yeah.
no definite answer. Sometimes I am like very hopeful, and sometimes I say, okay, it's like each time you see a new door, it just gets closed, and so
yeah.
But right now we have this door that is open. Like try to find a problem that you can solve with the polyalgebra.
Okay, yeah, that's good. Yeah.
It's not obvious that they will exist, but why not?
Yeah. Or even like, I mean, it could be possible that it's just outside the class of efficiently simulable problems. Like and maybe like they might be the first ones to get attacked by these tools. Yeah.
Yes. Okay.
Okay.
I mean, we're almost done here. I just wanted to speak a little bit about what happens at solutions. So I wanted to connect what we did with, like, where did it come from? Like what this paper, and I would just, this is where it comes from. Like it's very well known in quantum control that the rank of the Hessian at solution, for example, consider unitary compiling. This is like a 2005 result that the Hessian, you can write it like this, independently of the number of parameters, and this means that you're kind of factorizing the Hessian that is an infinite times infinite matrix, or a very large number of parameters times very large number of parameters matrix. You're factorizing with a very small matrix that contains like the non-zero eigenvalues. So the rest is null space. And they show this factorization for d squared, but in our case, where d is exponential in quantum computing, and this is like obsolete, right? And now but the final message is this null space. The manifestation is that the null space is the size of the solution space, the null space of the Hessian solution. And you can actually visualize it. This is one of the first works of mine on landscape, and what you see is, suppose you have the case of a rank of the Hessian is 2, and you put 3 parameters. Then you have one like kind of extra parameter, and this is just the dimension of the solution space. And if you put 4 parameters, you would see like two-dimensional manifolds and so on. So this is my explanation of why it's so easy to optimize in the overparametrized space. So the theorem in this paper is that in the general G, not a controllable case, it's not d squared, but it's just dimension of G. That is just exactly d squared when you have controllability. So again, everything is connecting properly. Okay, I want to thank everyone for being there so late at night and to be able to share my work with you. These are the nice people I've been working with for these two manuscripts. And okay, thank you very much. Are there any questions? I guess they were made in the way, but if there's a final question or something, I will be happy.
I mean, I guess anyway, these lectures are recorded. I mean, this talk, but like, do you mind just sharing the slide? Like, I mean,
of course, I can share the slides, and you can contact me whenever you want, and we can keep discussing. Of course, I know the time zone is kind of bad, but we can find the time, definitely.
So you're in the US at the moment, or
no? I'm in Argentina.
Okay.
In Argentina.
Okay.
For like couple of like weeks more, like month or so, and after Christmas I am going to Los Alamos for a PhD. I will like present my thesis like in a couple of weeks here, and then just fly it. So okay.
Thanks Martin for the wonderful.
Can I ask a question, or is it too late?
No, you can. No, of course it's not late. It's late in for you.
No, not for me. For me, it's not late. It's just time.
You're not in Singapore.
No.
Okay.
Okay. For your when you investigated trainability, I was wondering, so because whenever you show the controllability, for example, you always assume you have a random set of parameters, right? But I didn't understand wrongly. So what happens if you choose like a particular set of parameters? In that case,
like distributions that are like concentrated somewhere.
Yeah, correct. Like if you don't choose randomly, let's say an extreme case, like just setting everything to 0, right? Then I guess you don't have a trainability problem, right?
Setting everything to 0.
Like if you choose as initial condition of your training, you just choose.
That's terrible, because if you initialize at 0, that's very bad, I think, because your ansatz acts as an identity, and in that case, I'm quite sure you're already like very bad. That you cannot escape from there. That's I think is the worst possible choice.
No, this was an extreme case. Just saying that.
No, but
this, particular choices, not random, but
making particular
where
choices,
the trainability maybe still rise, but you still have some expressibility. But yeah, I agree. There's a trade-off.
Of course, our results do not like you cannot capture everything. It's just we assume, we make big assumptions and we try to derive analytical results. But of course, there are things that would escape from that.
Yeah, no, I'm just asking.
But it will be hard to
one approach. You could
it will be hard.
Even in a controlled
this
regime.
will be like definitely very heuristic, and it will be hard to prove anything about scaling of that choices, right? You can show it works for like low end numbers that you can simulate and whatnot, but proving the scaling of some like smart initialization, I don't think it's very easy possible, I guess. But I mean, it's interesting to study, of course.
Yeah, I remember there were some choices like where you correlate the parameters and you find some improvements.
Well, correlating parameters, you can see it you can see it just as changing your algebra, because, for example, let me show you very briefly, but how can I?
Yeah, right. I mean, of course, you choose a different algebra if you fix
for
the
example,
parameters to some.
If you correlate the parameters between like these two unitaries, these two gates, you will have a single 1 qubit like x plus z direction rotation, and this is a different algebra, and this is very similar to this. So yeah, correlating here, it's like going from here to here, but you can always think in the algebra and generator formalism. I think it's more clear than correlating, but it's actually equivalent in some sense.